Okay, so we have been spending some time talking about chemical equations, and now we've been talking about mole conversions. So now we're going to start something called stoichiometry, and it is honestly when you do balancing equations and mole conversions at the exact same time. So let's just get started. So first of all, what in the world is stoichiometry? Stoichiometry is the Greek word for measuring elements. We define it as calculations of the quantities, so how much you have in chemical reactions based on your chemical equation. So if you remember back, we would add coefficients to make an equation balance, which means we should have twice as much or 3 times as much or 4 times as much of a certain product or reactant. This is basically taken into account stoichiometry. So let's just do a practice. So mole to mole conversions, each time we use in this equation, 2Al2O3 will yield 4 aluminums plus 3 O2s. So if we look at these coefficients right here, we have a 2, we have a 4, and we have a 3. This means that every time we do this, we will have 2 moles of aluminum oxide. And when we have 2 moles of aluminum oxide, we are going to produce 4 moles of aluminum and 3 moles of oxygen. So the coefficients are technically telling you how much you have of each of our products and our reactants. Okay, so whenever we are doing this, we can again create a conversion factor. And if you remember, conversion factors are 2 equivalent measurements. So what we have just made up here, this is a balanced chemical equation, which means that this is how much reactant you need to produce this much product. So we can compare a few things. So in this reaction, 2 moles of aluminum oxide will produce 3 moles of oxygen. This is a conversion factor because these two things are equal. In order to get 3 moles of oxygen, we need 2 moles of aluminum oxide and vice versa. So just like other conversion factors, we can flip them around. 3 moles of oxygen produces 2 moles of aluminum. They are technically equal to 1 because it's the same amount of oxygen. It's the same amount of aluminum. Okay? Well, since there are 3 things in this equation, we could technically produce 2 more conversion factors. So let's say I wasn't going to oxygen. Let's see if we can create some for aluminum. I could make the conversion factor 2 moles of aluminum oxide over 4 moles of aluminum. Or I could write 4 moles of aluminum over 2 moles of aluminum oxide. Okay, so basically you have to use 2 of however many. Sometimes reactions have 4 reactants to products, sometimes they have 3, sometimes they only have 2, sometimes they have 10. But to make the conversion factor, you just have to choose 2, and they can be any 2. Alright, so we all like steps. We like to know how to correctly do stoichiometry. So what you do, the first thing you have to do before you can do anything is you have to make sure the equation is balanced. The couple we're going to do here in just a minute are not balanced equations. After you have a balanced equation, you have to convert the given amount into moles. The first step is to always do it into moles. Just like when we were doing our mole conversions last week, the only way we can do a mole conversion is if we convert it into moles first. Okay, after you have it into moles, then we need to change the compound. This is why I was so particular on when you use the unit mole, you have to put the compound after it because that can change your answer. We're trying to change the type of compound we're talking about. Okay, after we set up the mole ratios, we use the mole ratios to calculate the moles of whatever chemical we're trying to figure out. And then we go back into our final unit, which could be grams or volume or atoms or particles, just like we were doing our mole conversions last week. So this is kind of like our mole conversions on steroids. So let's just see if we can do a practice problem. So this is the same equation we were talking about just a few seconds ago. This one says how many moles of oxygen are produced when 3.34 moles of aluminum oxide decompose. So basically this question is wanting to know how much product we are going to get if we have 2.34 moles of aluminum oxide. So the first step in every single conversion is to write down what was given to you in the problem. So 3.34 moles of aluminum to oxide. Okay, where are we going? It's wanting us to go to moles of oxygen. Well, I don't know of a conversion factor that goes, well, I do. We just learned a new conversion factor. We learned a conversion factor that we can go from a moles of one compound to the moles of another. So in order to get rid of moles of aluminum oxide, I need to put that on the bottom. I want moles of oxygen on the top. So now I need to look at my chemical equation. The coefficient for oxygen is 3. The coefficient for aluminum oxide is 2. So now we're no longer going to have 1s in our conversion factors. So now we're going to take 3.34. We are going to times it by 3. And then we're going to divide it by 2. So 3.34 times 3 divided by 2 gives us an answer of 5.01. Our significant figures are correct because 3.34 has 3. Our answer has 3. Now we just need a unit. This is going to be moles of oxygen. All right, so let's see if we can do another example. All right. Yay, we did it right. All right, so the next problem. 2 C2H2 plus 5 oxygens is going to give you 4 carbon dioxides plus 2 H2Os. If 3.84 moles of this is burned, how many moles of oxygen are produced? So basically it's saying if we have 3.84 moles of this, how much oxygen are we going to need? Okay, so the first step in every single one of these problems is to write down what we're starting with. So we are starting with 3.84 moles of C2H2. Okay, we're going to put what we want over what we have. It's asking us to go to moles of oxygen. We are currently in moles of C2H2. You look at the chemical equation. There's a 2 in front of the C2H2. There is a 5 in front of the O2. So when I put this in my calculator, I'm going to do 3.84 times 5 divided by 2, and I get an answer of 9.6. Well, our answer had 3 significant figures, so we need to add another significant figure, so we're going to add a 0. Then we need a unit, and our unit is moles of oxygen, because this guy cancels out this guy, and we're left with moles of oxygen. But these are only one-step conversions, and you know we're going to do some more difficult ones. Okay, but let's try one more one-step conversion just to make sure we're all on the same page. So, this time around, we are going to produce 8.95 moles of H2O. And it wants to know how much of this are we going to need in order to get 8.95 moles of H2O. Again, we're going to write down what we're starting with. So 8.95 moles. You're going to put what you want over what you have. We want moles of C2H2. We have moles of H2O. We look at our chemical equation. There is a 2 in front of C2H2. There is a 2 in front of H2O. Luckily for us, we know something about 2 divided by 2 that's going to equal 1, so we shouldn't even have to put this in our calculator. But our answer should be 8.95 moles of C2H2. Alright, let's see what's in store next. Okay, so this one's a little bit more difficult. This time, we're not starting with moles. We are starting with grams. So this problem is the same basic problem, except we're not starting in moles. It says we have 6.5 grams of aluminum, and it reacts with an excess amount of oxygen. How many grams of aluminum oxide are formed? So it's wanting to know how many grams of this are we going to have. So this is a very complicated step. So the first step in every single conversion is to write down what was given to you in the problem, which was 6.5 grams. Okay, where are we going? We want grams of aluminum. We do not have a conversion factor that allows us to go from grams to grams. So we're going to have to do a whole bunch of conversion factors. Well, just like I've been saying, we can't do a mole conversion without first going into moles. So we have to go into moles first. So 1 mole of aluminum, if we look at the periodic table, has a mass of 26.98. Okay? Got rid of grams. Now we're in moles of aluminum. That's not what we want. We want grams of aluminum oxide. Well, we can't go, I don't know of a conversion factor that allows us to go from moles of aluminum to grams of aluminum oxide because we can't go from one compound to the next, so we have to change our compound. The only way you can change your compound is if you change your moles, so we have to do a mole ratio. We're going to put the moles of that we want. We want moles of aluminum oxide. We have moles of aluminum. So now we look at the periodic table. The number in front of aluminum is 4. The number in front of aluminum oxide is 2. So we have a 2 to 4 ratio. Okay, so this cancels out this. We're left with moles of aluminum oxide. That's not what we want. We want grams. So we have to do another conversion factor. Again, we're going to put what we want over what we have. We have moles of aluminum oxide. And I'm running out of room. We want grams. So I need to look at the periodic table. 1 mole of aluminum oxide. Well, aluminum is 26.98. We have 2 of them. Oxygen is 16, but we have 3 of those guys. So if you put this in your calculator, you get times 26.98 equals plus 16. We get an answer of 101.96 grams per mole. Okay, so now we go back up here and we can put the 101.96 into our equation now. So let's check and make sure all of our units cancel out before we put this all in our calculator. This guy now cancels out this guy. We're left with the grams of aluminum oxide, which is what we wanted. So now all we have to do is put this in our calculator. So we're going to do 6.5 divided by 26.98 times 2 divided by 4 times 101.96, and we get an answer of 12.3. And I had to round it to 12.3 to maintain significant figures. So again, I did 16.5. Let's change the color here. All right, so I did 6.5 times by 1 divided by 26.98 times by 2, divide that by 4, times by 101.96, divide that by 1. Again, that's why I saved the math until the very end, so I don't have to keep writing down numbers over and over and over again. And now we should be ready to write our answer down. 12.3, now I need a unit. The only unit we're left with, I circled, was grams of aluminum oxide. Now, I know this is a process, and I know that this is difficult, and there are a lot of steps. So if you get confused, just go back to the slide. Let's see if I can get back to the slide. Let's see, where is the slide? Let's just go back. There was a slide. It talks about the steps to stoichiometry. So if you get lost and you're trying to figure out how to do this, go back to this 5-step process. Balance the equation, convert to moles, set up the mole ratios, use the mole ratios to calculate whatever we're talking about, and then put it in the correct unit. So if you need steps, here are your steps. So what I would like for you guys to do is I want you to give this a shot all on your own. I want you to try to answer this question. I want you to figure out how many grams of ammonia are created through the reaction of N2 and 5.4 grams of H2. You need to, first of all, write a balanced equation. You need to convert the grams to moles. You then need to use the equation to find your mole-to-mole ratio. And then the last step is you need to convert the moles to grams. I want you guys to try this. Everybody better have an answer when I get here tomorrow. Okay? I want you guys to do this on, let's see here, I want you guys to do this on the back of your stoichiometry 3 square that the sub should have already passed out to you. When I get here tomorrow, I expect to see this completely done, and I expect everybody to have an answer. I don't care if your answer is right or not. It's perfectly okay if it's wrong, but I want us to have something that we can correct. So again, I want everybody to try this. You are more than welcome to ask your neighbor for help if you want to, as long as you keep the volume down.